So the world is a changeable and often unpredictable place, and organisms need to find ways of coping with this, whether they are trees or middle-aged professors with retirement accounts. Getting off of fortune's wheel is not an option, either in medieval thought or in biology, but there are some strategies for coping with this. One is to make fortune's wheel as small as possible, which is to say reduce variability. And this usually means a strategy that I'm going to call bet-hedging. Another possibility is to do really well in good times and poorly, but not really poorly in bad times, which is to say to raise or deform fortune's wheel. And I'm going to call this strategy go for broke. These are verbal descriptions for me to get more precise. I need to use mathematics. Fortunately, this is a math talk. So I get to say things that I probably couldn't to an ecology audience. Here's just a quick review. I have a discrete time model. N of t is the population at time t. So next year's population is this year's population times this year's growth rate, lambda t. So the population at time t is the initial population times the product of all the growth rates between then and now. And if we want to think about what is likely to happen to this population, we could take the average of both sides of this equation, but then we're taking the average of a product, and that doesn't work so well. So we take the log to break this up into a sum, and we find the fate of the population is determined by the expected value of log lambda. And I'm going to call that R bar, and refer to it alternately as long-run growth or long-run fitness. If we say that the growth rate in year t is equal to the time average growth plus a small perturbation epsilon, then we can Taylor expand the long-run growth out to second order and find that it's equal to the log of the time average growth rate minus a term proportional to the variance. And that's sort of at the heart of this talk. And so when we want to talk about increasing long-run growth or fitness, we can either do it by increasing the expected fitness or by decreasing the variance. And typically you can't do both. You have to choose one or the other. If you choose to reduce variance at the cost of a decreased mean, that's bet-hedging. If, on the other hand, you increase the mean at the cost of an increased variance, that's what I'm calling go for broke in this talk. Some quick definitions. When I talk about growth, I mean population growth, which is my definition for fitness. When I say environment, that's really short for an environmental response. That's any life history parameter that varies in response to physical conditions. So, for example, seed germination rate is going to depend on rainfall and temperature, among other things. Okay, so we have some additional twists that can come in. Growth or fitness is often a nonlinear function of the environment, either directly or indirectly via dependence on the density of other species. And that means that variation can affect the mean fitness as well as the fitness variance. Additionally, even in a constant environment, fitness can vary because individuals are lucky or unlucky. And depending on your disciplinary background, you call this demographic stochasticity, or internal noise, or shot noise. So I'm going to tell you 2.5 stories about variability. I used to put 3 stories in a talk, but costs are going up. The first asks the question, should plants be expected to increase or decrease variability in germination rates? And this is one of those cases where growth is a nonlinear function of the environment. And the second story asks, can variation due to luck select for bet-hedging? And spoiler alert, the answer is yes. However, many people would tell you no. And the half a story is an advertisement of things to come, looking at estimating the selective pressure for and against variability. Okay, so looking at that first story. one of the long-standing questions in community ecology is how can so many species coexist when they have similar resource requirements? And this question becomes particularly acute for plants because their resource requirements are in fact so similar. They require light, water, a dozen or so minerals. Part of the answer that people have given is that environmental variation can provide new mechanisms of coexistence. And the best known of those mechanisms is the storage effect. Here's a cartoon version of maybe the easiest way to get a storage effect. We imagine we have red and blue plants. In a good year for red has a high germination rate. Lots of red plants around replenishing the red seed bank, but most of the blue seeds remain dormant. In a good year for blue, it's the reversed. Blue has a high germination rate, lots of blue plants replenishing the blue seed bank. By seed bank, I mean all these seeds underground waiting to germinate in future years. And the red seeds largely remain dormant. And so by varying germination rates, these species are sort of time partitioning their environment, staying out of each other's way. But that raises a question. The environment is probably going to cause some variability in germination, but is there pressure to be more sensitive to the environment? So having higher variability in germination and going for a go for broke strategy, or should they be less sensitive to the environment? So you have lower variability in germination, more of a bet-hedging strategy. On the one hand, there's a cost. Variable germination rate increases variance and fitness. We've already said that that's a bad thing. But it could potentially increase mean fitness by allowing species to avoid competition via the storage effect. We might also have predictive germination, so that species germinate more in good years. A lot of seeds are not inert. They have sensors that can detect cues in the environment that will let them know, yeah, this is a good year, you should go for it. In this talk, a good year is going to be a high fecundity year. And so we have to weigh the penalty of variable growth against the possible benefits of predictive germination and a storage effect to see what will happen. Using a model with 2 annual plants, there's variable fecundity, that's that good year, bad year thing, and variable germination. Both of these vary stochastically, but not in a temporally autocorrelated way. I tried using autocorrelated time series and it didn't make a difference, so I kept it out. I'm assuming that variation is small relative to the mean, because this is going to be a perturbative approach. So just running through the model, the number of species J seeds at location X at time t plus 1 is equal to the number of seeds produced at Y. So here we have the number of seeds last year times the probability that they germinated and established themselves as adults, times the number of seeds they would produce in the absence of competition, discounted by competition, times the probability of dispersing from Y to X, so K sub J is a dispersal kernel, summed over all source locations J, and then we need to add in the dormant seeds that survived from last year. So 1 minus G means you didn't germinate, times S, the probability that you did survive. Competition is also given by convolution. We have the number of species K plants at Y, so here, again, we have the number of seeds times the probability that they germinated and established. Taken in a weighted average, this is a convolution with a competition kernel, times the competitive strength of species K against species J, and we need to sum over all species. I only have 2 species in this model, so the sum only has 1 term. Okay. Long-run growth to second order is a big hairy mess, but what's important to see is that variability does affect the mean fitness, and it affects it in ways that kind of make sense. So here's the covariance between germination and fecundity. If you germinate more in high fecundity years, this covariance is positive. A1 is positive, so that's predictive germination. Predictive germination is a good thing. It raises the mean. Here we have a covariance between germination or fecundity and competition. That's going to increase mean fitness if the covariance is negative. This is at the heart of the storage effect. The idea is, let's go back to that blue and red example. Suppose I'm a blue plant, and I am, for whatever reason, at low density, in danger of going extinct, locally extinct. But it's a good year for blue. Okay, so we have high germination, maybe high fecundity. I also have low competition. It's a good year for blue, which means it's not a good year for my competitor red. So I'm getting very little competition from red. But blue is at low density, so I'm not getting much competition from other blues either. So I have a good environment, low competition, so a double bonus. And the way the model is set up, growth is a concave up function of competition, so variation in competition is also good. On the other hand, all of these terms also appear in the fitness variance. So they raise the mean, but they also raise the variance. It's hard to see what's going to win at this point. Rearranging just a little bit, here's predictive germination, covariance between germination and fecundity. A1 is positive, so that's raising the mean, but it's discounted a little bit because of the penalty for variation in fitness. Here's the storage effect, the covariance between germination and fecundity with competition. Again, this will be negative. It's increasing the mean, but not as much as it might have without that variance penalty. We also just have penalties, straight up penalties with no benefit to the mean at all. This is the variance in germination. Here's the variance in fecundity. I'm using Fourier analysis, so I can go back and forth between talking about variances and covariances to talking about the power spectra of population and environmental fluctuations using the Wiener-Kinship theorem. And I'm using transfer functions to express the Fourier transform of population fluctuations in terms of the Fourier transform of environmental fluctuations. So ultimately, everything is in terms of the spectra of environmental fluctuations. Okay, so just to remind you where we were going with all this, we were wondering which wins out. Is it the penalty due to variable growth, or the benefits due to storage effect and maybe predictive germination? I've got two species here, and I'm trying to make an evolutionary argument. And so really I should be thinking about coevolution, how they respond to each other. So let's talk briefly about coevolution. To find the co-evolved germination variance, again, I'm imagining red and blue plants. First, I find the optimal red germination variance as a function of the blue germination variance. To do that, I consider a red mutant, this guy over here on the right. This is actually red, believe it or not, among coexisting blue and red wild types. I'm going to hold the blue germination variance constant and then adjust the red germination variance until the system can't be invaded by a red mutant. And actually what I'm doing is taking partial derivatives and finding maxima, but effectively that's what's going on. All right, so the best choice the mutant can make is to adopt the strategy of the red wild type. It's going to do what everyone else is already doing. And that gives me a curve something like this. I say species 2 is blue, and for every species 2 germination variance, there's a corresponding optimal species 1 germination variance. And then I switch roles. So now we're finding the optimal blue germination variance as a function of red germination variance. Considering a blue mutant now, holding the red germination variance, and adjusting the blue germination variance until the system can't be invaded by a blue mutant. Again, the best choice the mutant can make is to adopt the strategy of a wild type. So this is an environmentally stable strategy. So now I've got another curve. Here's species 2, the red species. Here's what species 1 should do in response if it could. And then we just overlay the curves. find where they intersect. And of course, make sure that the system can actually get there dynamically. So here, and this is convergently stable, here's where we would expect that system to lie, if it's free to evolve. Okay. So I've got some factors I can play with. One is to ask how much species preferences overlap. So I could say that species have their highest germination rates in the same years, or I could say that species have their highest germination rates in different years. If they have different preferences, that's when you expect to maybe see a storage effect, because they're time partitioning the environment. With fecundity and germination can be uncorrelated, or they can be positively correlated. If they're positively correlated, that's what I mean by predictive germination. So, 4 possibilities. Let's first consider the case where a storage effect isn't going to come into this. It's just more or less predictive germination. So here, species experience their highest germination rates in the same years. And we see that, yes, as the correlation goes up, so germination is increasingly predictive. The optimal variance of both species increases, but these numbers are pretty small. There isn't much variance. So predictive germination alone can allow variable germination to co-evolve, but only at low levels. And that makes intuitive sense. It's a good year. We know it's going to be a good year, so everybody germinates, but now it's also a high competition year. And so what you gain in high fecundity, you lose because of high competition. But what if they prefer different years? Okay. Now we see much higher numbers for optimal variance. And these are high enough that you shouldn't trust them because they invalidate my perturbative approach. But the important thing is that they go up, and even more importantly, they actually go all the way down to 0 as we dial back predictive germination. So that means that a potential storage effect is in fact not enough to allow variable germination to co-evolve. Put another way, without predictive germination, we expect plants to minimize germination variance, thereby reducing opportunities for coexistence via the storage effect. Here's how I think about this. Here we've got, again, in a red and a blue wild type, and this lighter line is a red mutant. And on the left, the mutant has lower variance. On the right, the mutant has higher variance. I don't actually use periodic environments for this talk, but it's a lot easier to see the picture if I do that for now. Okay. Increasing variance increases the mutant's exposure to the same species wild type relative to the other species. Over here, it's spending almost all its time in the presence of red, and very low abundance when blue is sort of active. This could be good or bad, depending on how much competition the conspecific exerts. So I'm going to say that normally one species is the main source of competition for both species. Let's say it's blue in this case. And so blue evolves, or should evolve, decreasing germination variance, because it's trying to avoid itself. So it spreads itself out over years more evenly, but that means that the benefit of variable germination for red decreases, because if blue is spread out more evenly, there are no temporal refuges for red anymore, or fewer of them, so red's variance decreases. And they just end up ratcheting down. So here's what it looks like graphically. They only intersect at 0. So for example, if species 2 started off with a variance of 0.6, then we would expect species 1 have a variance of 0.8, 0.8, and now species 1 is here, and we expect species 2, say that's 0.15. 0.15, we expect species 1 to have an extra small variance, and it just walks down to the origin. On the other hand, one species can't evolve, the other will evolve some level of variable germination. So in summary, as germination becomes more predictive, higher levels of germination variance co-evolve. Not terribly surprising, predictive germination is a good thing. But predictive germination alone can only select for small levels of germination variance. Variable germination cannot co-evolve in the absence of predictive germination in this model. And probably you can't evolve zero germination variance. I mean, you need a certain amount of water and heat to germinate. But to the degree that plants can minimize germination variance, this reduces the effectiveness of the storage effect as a coexistence mechanism. And getting off into a more speculative realm, I think it should be even more difficult to co-evolve increased germination variance without help from predictive germination if there are more than 2 species. With 2 species, you can perfectly divide the environment into my time and your time. The more species you have, the more overlap in activity you're going to have. So getting on to story 2. Talk about luck. So what I've been talking about so far, and what most people talk about when they refer to bet hedging, is what's known as between generation bet hedging. There are good years and there are bad years. They affect everybody the same way. So here we imagine we've got 4 clutches of 4 eggs each. And in a good year, the expected fitness is 3/4. So everybody here, 3 out of the 4 chicks survive. In a bad year, we only expect to see 1 chick out of 4 survive. Because the good and bad years are affecting everybody the same way, there's a lot of variation in offspring number from year to year. And therefore, large variation in fitness. However, there's also within generation bet hedging, potentially. So each group is expected fitness is the same. It's 0.5 in both years. But each group is independently lucky or unlucky. So here, clutch 1 got lucky. Clutch 2, not lucky. Year 2, their fates were reversed, but the total number of offspring was the same. That means that total offspring production is going to vary only a small amount, unless the population is small, and then you've got some sampling variance. John Gillespie talked about this in 1974, and what he found was that the penalty for fitness variation scales as 1 over the population size. So that's that sampling variance coming in. So it really doesn't matter, unless the population is quite small. However, this is a really intuitively powerful idea, and a number of people have felt like it should be true. Enough people that there was a complaining sort of review written in 2003 by Hopper et al., who noted that, again, fitness advantage varies inversely with population size, becomes vanishingly small at even modest population sizes. They said confusion persists, bet hedging as a seductive explanation. At another point in the article, they talk about it being a siren song and wishing it would just go away, but basically this whole paper is saying, look, I know you really want this to be a thing, but it's just not, and please stop talking about it. But it can be a thing. It can be true. Turns out that within generation variation can matter if offspring fates are correlated. So here's the biological context that I'm thinking about. My collaborators, Scott Burgess, and Wojciech Wojcinski, Scott thinks about these rocky coast-dwelling marine invertebrates. This is a sandcastle worm. Each one of these little tubes hosts a worm. And when they spawn, they produce this huge cloud of gametes, which develop into tens of the many larvae, and to first approximation, the larvae drift on ocean currents until they finish development. At which point, if they're lucky, they are near viable habitat, they can swim out, begin to try to recruit as adults. If they're not lucky, they have been swept offshore, and they are never heard from again. This is, if you had asked me about this a year ago, I would have said this is probably the least likely place that I would have thought demographic stochasticity would matter, because there are just so many individuals involved. But it turns out that larval fates are not independent. Ocean circulation is highly stochastic, but it's not unstructured. You have these eddies at multiple spatial and temporal scales. And David Siegel's group at UCSB says that their simulations show that eddies funnel larvae into water packets, which are relatively coherent. And so these larvae travel together over the course of their development, and they either succeed or fail as a group. So the number of independent units here is actually much smaller than you would have supposed. So here's our population model. There's a fecundity size trade-off. You produce F naught over S offspring, where S is the initial larval size. So you can either produce a large number of small larvae or a smaller number of big larvae. Smaller larvae take longer to develop. So they spend a longer time at sea. They're less well provisioned. And they experience a constant mortality rate while at sea. So our fecundity size trade-off becomes a fecundity survival trade-off. Lots of poorly surviving larvae or a few better surviving larvae. The Oceanographic model comes from Siegel et al. The larvae in one water packet succeed or fail as a group, and so we have a binomially distributed number of successful groups. And to first approximation, one water packet equals one eddy. And taking this straight from their 2008 paper, then the number of packets is equal to the spatial domain of my system divided by the eddy size multiplied by the spawning duration times over eddy lifetime. It's the number of eddies we can sort of pack in that space and time period. We also have an evolutionary model. I think it comes from 11th set it out. We have an effective per capita fecundity B of S, where S is larval size. By effective fecundity, I mean you survived long enough to reach habitat if you were lucky enough to actually be directed there. But you survived your development period. The number of water packets is M of T, where T is the spawning duration. And the probability that a water packet will hit viable habitat is H. And the population of type J, I'm considering two competing types that differ in S and T, is N sub J. And so the expected fitness of type J is equal to the expected number of successful water packets, M times H, times the number of larvae per packet. So number of larvae produced is per capita fecundity B times number of parents N divided by the number of packets. What really matters here is that this is proportional to N, so we're just calling this mu times N. Likewise, the fitness variance is equal to the variance of the number of successful packets. There's the binomial variance, times the square of the number of larvae per packet. And what's key here is that this scales as n squared. And that really is mathematically where all of this is going to come from. Typically, variance due to demographic stochasticity scales as population linearly. And here it's this square. So underneath this, there's a branching process, but we very quickly switch to a diffusion approximation because it's ever so much more tractable. Depending, again, on your disciplinary background, you might call this a forward Kolmogorov equation or a Fokker-Planck equation. All it is we have the probability distribution of being at N1 population for type 1, N2 population for type 2 at time t. This distribution is changing in time. It's advecting, it's drifting in N1 and N2, and there's also a diffusion term.
What are the new variables? What are the relations?
Are there U's in here? So the expected fitness is mu times n, and the fitness variance is sigma squared times n squared. And that's where those come from. I don't actually care about the number of type 1 and type 2, though. What I really care about is, are we getting to be more and more mostly type 1 or more and more mostly type 2? Which one of these is sort of taking over? And so we're going to change variables to p, the proportion of the population that is type 1. If p is heading toward 1, then genotype 1 is heading toward fixation. If p is heading toward 0, then type 2 is winning out. And of course, n, the total population. And after really more work than it should have been, you get to the final equation, which is a mess. But fortunately, all we really care about is this bit here. So again, you can put this in advection diffusion form. It's drifting either toward p equals 1 or p equals 0. The population size is increasing or decreasing, and then there's the variance of this distribution is increasing or shrinking along various axes. What I really care about, though, is p. Is it heading toward p equals 1, p equals 0, and at what speed? And the speed of the drift is right here in red. Okay, so we drift toward higher p, more of type 1 at that rate, which has a lovely biological interpretation. We get more of type 1 when mu1 is bigger than mu2, so that means type 1 has a higher expected fitness, or when type 1 has a lower fitness variance than type 2, weighted by prevalence. Because p is the prevalence of type 1, and 1 minus p is the prevalence of type 2. So we are right back at that bet-hedging dilemma that I talked about at the very beginning. We can increase the prevalence of type 1 by increasing the expected fitness or by decreasing the fitness variance. I want to talk about the implications of this, however, for those two biological parameters we talked about, the larval size and the spawning duration. If you increase the spawning duration, so you're dribbling out offspring over a longer period of time, it doesn't change expected fitness at all, but it decreases the variance, because now you're dividing a fixed number of offspring among a larger number of water packets. So you're dividing your eggs among a larger number of baskets, if you will. So this is good. Lower variance is good. We should expect to see an increased spawning duration. Larval size is tricky. Fewer, larger larvae decrease expected fitness, not good. But they also decrease fitness variance, and that is good. So here's our bet hedging trade-off. Okay. Which one is more important? It's the variance. And the reason is because expected fitness scales linearly with effective fecundity, but the variance goes as effective fecundity squared, and these are marine organisms. Effective fecundity can be quite large. So reducing the variance tends to trump increasing the mean, and so you would expect to see a larger, fewer larvae. And you might ask, though, are smaller larvae ever favored? What would it take? So smaller larvae are favored if increasing expected fitness becomes more important than decreasing the variance. The variance will be less important if the effective fecundity decreases. So if we had higher larval mortality while at sea, or we spent a longer time at sea, a longer pelagic larval duration in terms of marine biology. It would also be true if the number of water packets decreases, because it turns out, not unexpectedly, that the variance scales as 1 over the number of water packets. So that would mean a large spatial domain or smaller or shorter lived eddies, so that would depend on the oceanography. we tried this with some data for echinoderms, and we found that at least for these values, variance always dominates. You want larger larvae, except for the lowest fecundity and the very largest spatial domain. So in summary, demographic stochasticity can produce bet hedging, or put another way, within generation bet hedging can be important for large populations. And that happens when the reproductive output of the entire population is divided into a number of groups that is independent of population size. So we might expect to also see this, for example, in a terrestrial system, if you had patchy habitat of fluctuating quality, you have seeds which are dispersed, sort of land randomly among these patches, and some of them land in good patches and some of them land in bad patches, but the number of patches is fixed. Okay, so now we have a half a story. Advertisement. So some years ago, I started working with Peter Adler and Steve Elner. Peter has this lovely 22-year spatial data set, and with Steve, we created a fitted model of the 4 dominant plants. There's this sagebrush bush and 3 types of bunch grasses. And this is an integral projection model, which means that the size distribution this year is equal to the size distribution last year, convolved with a kernel. And there's a different kernel for each year, for each species. So we have variability in things like survival and growth, and reproduction. I heard about this and I said, cool, I could do a numerical experiment and see, like, is there pressure for more variability or less variability in a real system? And to do that, you would increase or decrease the variation in growth, survival, and recruitment in turn, so that the new standard deviation is equal to some scaling factor kappa times the old standard deviation. Simulated the system by sampling with replacement from the 22 year types to find the long-run population growth rate, and regress that long-run population growth rate on kappa, and average the slope over 10 repetitions. That becomes 10 replicates. That becomes the strength of selection. So if growth rate goes up as we increase variation, that's pressure for more variability. If growth rate goes down with variation, that's pressure for less variability. And I'm going to run through the results fairly quickly, because honestly, they're just a setup for a plot twist. We found selection against variation in growth and survival, but selection for variation in recruitment. We asked if species interactions affect selection. Sometimes. And do the interactions affect selection because of variable competition? That would be required for something like a storage effect. Answer, absolutely not, quite unequivocally. It's like, okay, species interactions matter, but variable competition, it's just the mean level of competition that matters, not the variation. So all of this selection for and against is coming from nonlinear averaging. Great. Presented it at a conference, got ready to write it up, and then realized that the functions we had on our model were not chosen, their curvature, concave up or concave down, wasn't chosen because of the data, but because these are what one normally uses in these models. They're chosen largely for statistical convenience, and so we got out what we put in. End paper. We also realized that that's what everybody else was doing as well. So, begin grant proposal. So there's the but. The grant proposal probably got funded. We still don't have official word from the NSF. We have unofficial word from the NSF that it got funded. And so part of the work of that proposal, we've now brought Giles Hooker from Stats Department here at Cornell onto the project to think about how do you ask the data what kind of curvature these reproduction and survival curves should have. And when it's all done, I'll be able to go back to my numerical experiment and finally finish that project. Among many other things that grant is meant to look at. Okay, so I want to leave you with some last thoughts about variability. high means often come with high variances. And this is why we get bet hedging, we get balanced investment portfolios, all these sorts of things. So we often end up sacrificing some expected fitness for a lower fitness variance. And you can think about this as bet hedging. You could also think about this as being a temporal generalist. You do middling well most of the time. Not super great in good years, not terribly bad in bad years, kind of a jack of all trades. However, if growth or fitness is a nonlinear function of the environment, then variability can increase in expected fitness. And so sometimes higher variability is a net positive. This is the go for broke strategy. You could also think about it as being a temporal specialist. You are geared up to do really well in certain years, even though it means you do really not well in other years. Finally, variability due to luck normally can't produce bet hedging unless the population is very small. However, there's an exception, and that's when offspring succeed or fail in groups, and the number of groups is independent of population size. And with that, I'll thank my collaborators. Peter Adler was involved in the first story about evolving a storage effect. Scott Burgess and Wojcicki were involved in the diffusion approximation within generation bet hedging. And of course, Steve and Peter and soon Giles will be involved in the project that we're just beginning. Thank you very much.
We have time for questions.
So, a naive question about risk sensitivity, right? One context in which I know about it is stochastic optimal control, where people, the most traditional approach is to minimize the expected total cost. But if people want to take into account the risk,
Okay.
they minimize the expectation of the nonlinear utility function, where the degree of convexity does something very similar to
Okay.
what logarithmic term does in there.
Nice.
But they also have a parameter in there floating, which basically is the degree to which you're sensitive to risk, how convex.
Yes. Very nice.
Do you have anything like that in here? Are there
I think-
biological, ecological reasons to say this one is more risk sensitive, that one is less?
Yeah, I mean that's, as you've stated, it's gonna depend on the curvature of these, say, recruitment function or survival function, and you can kind of tell stories about those curvatures. So I could imagine, for example, that if this is increasing goodness of the environment, however we want to define that, and this is reproductive potential, that in a really bad environment you just can't reproduce at all, so that's 0. And then at some point it gets good enough that you can reproduce some, and my intuition is that initially the marginal value of improving your environment is fairly high, so this goes up steeply, but there comes a point where it curves over and you can only devote so much energy and biomass to reproduction, and so it really doesn't matter anymore how good your environment is, and so the marginal value drops off, and so that's going to be a concave down function, and so I would expect to see selection against variability in recruitment. Now this is the opposite of what we found in the IPM, because that had a concave up function, but you can kind of tell stories like, so that in that case it would be a system of, how quickly is this going to bend over? That would be something about the sensitivity to variability. Other thoughts? Yeah.
Yeah. So coming back to your luck, this is story 2.
Yeah.
Okay. So you talked about how it depended on whether total fecundity was large or small.
Yeah.
But really, total fecundity is per capita fecundity is always 1. Unless, right, that on average each individual in generation n produces one individual in generation n plus 1.
Yeah, I was
Okay,
using a
so-
linear model, and this is nonlinear.
Okay, so,
yeah,
so
yeah,
my
yeah.
question is, how much of what you're seeing do you think it would persist if you took into account that at some point there has to be some density dependence acting so that you can't continue?
Yeah.
Right, a branching process goes into exponential growth. A real population never does.
Never
It has to
levels
saturate.
off. Ooh, I like this very much. And you come at an apt time because I'm writing this up right now. That's cool, because then I think you might see a shift away from the variance trumping all other concerns and start to see expected fitness. So I'm wondering if the population were at really low density, because of overfishing, or it's actually an invasive species and it just got introduced, that you see a risk minimizing strategy, and then as it starts to get into that density dependent phase, if it's more about increasing mean fitness, that would be really neat. I don't actually know, but it's my gut sense.
All right. If there are no further questions, let's thank Robin again and head for the refreshment.